Hello, my name is Theodore Awad and I'm excited to show you the binary morphological neural network. This work has been accepted at the International Conference on Image Processing 2022. After the introduction, we developed the necessary notions to define the Bayes neuron. Then we show the experiments. Finally, we conclude and present leads for future research. Convolution is an operation that applies a local filter to an image, and the filter depends on the task to solve. It is a linear operation and has shown incredible results, especially if stacked sequentially, in many different applications, such as image denoising or edge detection. Convolutional neural networks allow to learn the best filter for a given task. However, for certain applications, morphological operations based on dilation and erosion are better suited. They are similar to convolution in the way that they also use a local filter called the structuring element. Still, finding the best sequence of operators and the right structuring element can be difficult. We focus on binary inputs. In this work, we see how we replace the convolution of convnets by learnable morphological units to create morphological neural networks. We introduce the binary structuring element neuron, or Bayes neuron, that can learn both dilation, erosion, and the structuring element. By stacking them, we can even learn more complex morphological pipelines. I begin by introducing some notations. We will be placed on the grid ZD. In this work, D equals to 2 for 2D images. However, everything will work for any D, in particular 3 dimensions. An image is a function that associates to each pixel a value in R or in 0, 1, depending on the context. A shape is defined as a subset of ZD, and it can also be seen as a binary image with its indicator function. S will be a morphological structuring element and is also a shape. Therefore, it can also be seen as a binary image. Finally, we denote the convolution with the circle dust symbol. The convolution and elementary morphological operations are closely related. Let X be a shape, and let us take the dilation for the sake of the example. So we compute its dilation. Now we see X as a binary image and compute its convolution with S seen as a binary image. We compute the convolution pixel by pixel. Now on the resulting image, we only keep the pixels that are higher than 1, and we see that we recover exactly the dilated image. The same can be done with the erosion, with only the value of the threshold changing. Finally, we conclude that morphological operations, dilations and erosions, are thresholded convolutions. Convolution and morphology are local operations. Let us focus on one output pixel. The result only depends on the neighborhood of the input pixel. Therefore, we can focus our study only on neighborhoods that are the size of the structuring elements. This equivalence holds for any binary input x. Now let us try and generalize this equation. We replace the threshold by a real value b, and we replace the binary s by a real weights matrix w normalized between 0 and 1. What is the relationship between w and b that still ensures us the equivalence between morphology and convolution? We suppose that the equivalence between convolution and morphology holds. Then, by choosing specific inputs, we can derive inequalities between w and b. For example, let's take x being 1 pixel inside of S. Then the dilation is equal to 1, and the convolution, because of the assumption, is higher than b. Then we can derive an upper bound for b. This can be done for any pixel inside of S. This gives us the lowest upper bound for b. The same can be done for an input, such as the dilation is equal to 0. And then, according to the assumption, we have a lower bound for b. These two bounds are a necessary condition for the equivalence to hold, and it turns out that there are also sufficient conditions. Similar bounds can be derived from the erosion with the same reasoning. The bounds we just found are values taken by the convolution for certain inputs. Let L be the lower bound, and let U be the upper bound. We will analyze the convolution outputs depending on different inputs. between the minimum and the maximum. The position of the point will be given by the convolution output value, and its color by whether it is inside the dilation or not. We exhibit the morphology convolution equivalence. If the output value of the convolution is higher than b, then the point is inside the dilation. If the convolution output is below b, then the point is not inside the dilation. Moreover, we can see that there is no value between L and U. For any given input, the convolution is either below L or above U. Let us define some W and B that respect the inequality we have just found for the dilation. Then we can recover the structuring element by thresholding W. The threshold depends on the operation. We now have everything we need to introduce the binary structuring element neuron, or B's neuron. We have seen that the morphological operations can be seen as thresholded convolution. We will focus on the thresholded convolution parts. First, we replace the strict binary input with a normalized one between 0 and 1. Then we enforce the normalization of W with a smooth threshold function of a real parameter omega. By passing B on the other side, we just need to replace the hard threshold function by 0 with a smooth threshold function that we have already defined. Finally, we multiply what's inside with a scaling factor p for practical reasons that will be explained later on. And there you have it, the definition of B's, with learnable parameters omega, b, and p. Finally, if the inequalities of the equivalence are respected, we say that the B's is activated for S and for the corresponding operation. And then we can say that the B's has actually learned the structuring element S as well as the operation. We suppose the B's is activated and we place the bounds on the graph. Then we analyze the B's output depending on the convolution. Let V1 and V2 be the values taken by the B's for the convolution value L and U. Then, as there are no values between L and U, the output B's is either below V1 or higher than V2. Then we see that V1 and V2 are highly sensitive to P. The higher P, the closer the output is to a binary output. This motivates the definition of almost binary images that are either below a value V1 or above a value V2. If I is an almost binary image, then Xi is its associated shape. The paradigm has changed. Now, instead of dealing with strict binary images, we deal with almost binary images and their associated shapes Xi. We have seen that if a bit is activated, then for any binary input, the output is almost binary. Then we want to give this almost binary output to another bit as inputs in order to stack one bit after the other. This begs the question, what happens if the input is not strictly binary but almost binary? Let's look at our previous results and see how they can be adapted to almost binary images. First, the equivalence between morphology and convolution can be rewritten in almost binary form. Then a new inequality can be derived taking into account V1 and V2. The same can be done for the erosion. Then, the structuring element recovery by thresholding can also be adapted by changing the threshold and adapting it with V1 and V2. Finally, if the base is activated, the output of an almost binary image is also almost binary. We can now define the binary morphological neural network. It is just a set of sequentially stacked B's applied one after the other. The parameters of the different B's are optimized using the backpropagation algorithm. We have introduced the B's neuron that can learn both dilation and erosion and the structuring elements. We have stacked this neuron to create a binary morphological neural network. Let's focus on the first B's of this network. Its input is a binary image, which can also be seen as an almost binary image with values 0 and 1. Let's say that we are in the middle of the training and we have these parameters. We want to check if the B's is activated or not. To do so, we check different candidates S and see if the bounds are respected or not. Instead of looking at all possible candidates S, we have seen that it is sufficient to look only at two specific S that can be found by thresholding the weights with specific thresholds depending on the operation. We can test only these two structuring elements. And if neither works, we can conclude that the base is not activated. And then we can just keep on training. Now let's check with another set of weights and bias. Again, we check only these two structuring elements. So for the erosion, we see that it doesn't work. And for the dilation, we see that indeed we have the bias inside the bounds. We conclude that the B's output is almost binary, with these new values defined. Then we can do exactly the same thing we did for the second B's neuron by updating V1 and V2 with the two values we have found. If the base is activated, by definition we have the following equality. Now the left-hand side is equivalent to the base higher than 0.5. And as the base is almost binary with V2 higher than 0.5, we can deduce the following equality. This means that the base in the almost binary realm is equivalent to a morphological operation in the binary realm. I is the same as xi, and after the operation, the outputs are the same. Let's do some experiments. We will use different datasets. First, we define a generated toy dataset called discorrect. To generate a sample, we add a predefined number of shapes that are either rectangles or ellipses. Then we add holes of the same type. We add Bernoulli noise, and we invert the output half the time. The second dataset we use is an upsampled version of NIST that is thresholded. Finally, the last dataset is its inverted version. We try to learn different operations. First, for the erosion and dilation, the network will be composed of a single B's neuron. Then, for the opening and closing, the network will be composed of two B's neurons stacked one after the other. We will try three different structuring elements. The goal is to learn both the structuring element as well as to activate the B's. We will analyze the learned weights as well as if the B's are activated or not. Finally, we use the dice loss for the discorrect dataset and the mean squared error loss for the NIST dataset. Let's see the results after convergence. We start with the erosion and dilation. We show the learned weights. The number below indicates the dice error. The check indicates if the base is activated or not. First, we notice the error is at 0 everywhere. Some are successfully activated and others are not. Finally, in some cases, we learn the frontier of the structuring element. This is not a problem, as the resulting image is almost the same. For the opening and closing, we managed to learn the cross and the stick from most datasets. However, the disk remains hard to learn. Opening and closing are dual operations, which means they are closely related. Ideally, we would like the training of these two operations to be the same. However, this is not the case in practice. To conclude, the B's neuron can learn both erosion and dilation, as well as opening and closing in most cases. For future work, we will study the initialization of the B's to have identical dual training and to avoid gradient vanishing for deep networks. We also want to binarize the network even if the B's is not activated. We will reach more complex morphological operations such as top hats by adding intersection, union, and complementation of operators. Finally, we will extend this network to grayscale morphology. Thank you very much for your attention, and if you have any questions, please don't hesitate to ask.